scientists heard a shudder in space-time that lasted about 1/10 of a second. That was enough to tell us that somewhere billions of light years away, two black holes had just smashed into each other. That part is already extreme. But the real shock is this. According to the old picture, black holes like these were not really supposed to be there in the first place. The event known as GW231123 was announced by the LIGO-Virgo-Cagra collaboration in 2025 as the most massive confidently detected binary black hole merger so far, with component masses inferred at roughly 137 and 103 times the mass of the Sunday. So this is not just the story of a collision. It is the story of a cosmic rule that may have just failed. Because for years, astronomers had a pretty clean idea of how black holes like this should form. A giant star lives fast, burns through its fuel, collapses, and leaves behind a black hole. Simple. Except nature has a habit of taking our simple pictures and using them until they break. And in this case, the thing that broke the picture was not a telescope image, not some glowing explosion in the sky, but a tiny ripple passing through Earth itself. GW231123 was detected on the 23rd of November 2023 in both LIGO observatories, and the signal was strong enough to stand well above the background with a network signal-to-noise ratio of about 22.5. We never saw these black holes. There was no bright flash, no visible, no cosmic debris cloud lighting up the sky. Because black holes do what black holes do best. They hide. They trap light so completely that by the time two of them merge, the most dramatic part of the event can happen in total darkness. And yet, the universe still leaves a trace. When two black holes spiral around each other, they stir space-time itself. Not the gas around them, not the light coming off them. Space-time. They make the universe ring. And LIGO was built to hear that ringing. LIGO's 2US detectors work together to identify gravitational wave signals, measuring incredibly small distortions caused by violent events like black hole mergers. That is one of the strangest things modern science has ever achieved. Human beings built an instrument on one planet, around one ordinary star, in one average galaxy, and used it to detect a dark collision from across the universe. If you want a body scale way to feel that, imagine hearing a floor creak in your house and discovering it was caused by a mountain collapsing on another continent. That is the scale mismatch here. Tiny clue, enormous cause. And when scientists decoded that clue, the first surprise was not just how large the merger was, it was who the two black holes seemed to be. The combined system came in at roughly 190 to 265 solar masses, and the final remnant was around 225 solar masses, making it a clear intermediate mass black hole candidate. Before this, the most massive, confidently observed binary black hole mergers were lower than this. That alone is a huge deal. But now comes the part that makes this video worth watching. The parent black holes, the two objects that merged, appear to sit in what astronomers call the pair instability mass gap. That phrase sounds technical, but the idea is surprisingly simple. There is supposed to be a missing band in the black hole family, a stretch of masses where the usual story says black holes should be rare or absent, because stars in the right range do not die neatly enough to leave them behind. LVK's public paper on GW231123 describes both components as likely lying inside this pair instability mass gap. So picture a staircase. You expect steps at the bottom, you expect steps higher up, but somewhere in the middle, one section is missing. That missing section is the mass gap, and GW231123 looks like two black holes standing right on those missing steps. That is why people started calling them impossible. Not impossible in the sense that nature forbids them forever. Impossible in the much more interesting scientific sense. Impossible according to the cleaner version of the model, and that is always where things get good. Because once nature does something your model did not expect, you get to find out whether the universe is breaking the rule, or whether your rule was too simple. To understand why astronomers expected that missing band at all, you have to go back to the stars that make black holes. Not every giant star becomes a black hole in the same way. Some collapse and leave behind a compact remnant. Some explode and shed a lot of their mass first. And some of the biggest ones are thought to enter a more violent regime, where the physics inside the star becomes unstable enough that the star can blow off huge amounts of itself or even destroy itself so completely that there is no black hole left in that mass range. That general expectation is what produces the pair instability mass gap in stellar evolution models. In plain English, some stars are too big to die quietly, but not big enough to skip the mess. So instead of leaving behind black holes in this middle range, they are expected to disrupt the process. That gave astronomers a clean picture. Lower mass stellar black holes? Sure. Much bigger black holes through other pathways? Also possible. But in between, there should be a kind of desert, a sparse zone, a missing strip in the lineup. And then this signal arrived and basically said, "Are you sure?" Because GW231123 did not seem to contain one black hole brushing the edge of that forbidden zone. It seemed to contain two. That is the first major payoff of this story. Not one outlier, a pair, a matched set of troublemakers. And if that were not enough, the signal carried a second problem hidden inside it: spin. The data indicate that both black holes were highly spinning, near the upper end of what black holes can physically support. That high spin inference is one reason the event has been difficult to model and interpret cleanly. This matters because once astronomers saw the masses, the obvious rescue idea was easy to imagine. Maybe these black holes were not born directly in the gap. Maybe they started smaller. Maybe black holes in a crowded environment kept merging with other black holes, growing larger step by step, until eventually two big ones met and produced this signal. That kind of chain reaction is called hierarchical merging. And at first glance, it sounds perfect. If the forbidden band is hard to reach by ordinary stellar collapse, maybe you climb into it by repeated mergers instead. Problem solved. Except the spins make that solution much less comfortable. Because when you keep building bigger black holes out of older mergers, you do not automatically get exactly the combination of extreme mass and extreme spin that GW231123 seems to show. The easy answer starts to wobble, and that is the moment where the real mystery upgrades. The mass was already bad enough. Then the spin made it worse. That is the point where this stops being a story about one giant collision and becomes a story about black hole birth itself. Because if the standard stellar route struggles, and the neat repeated merger route also struggles, then maybe the real answer is hiding earlier in the story. Back at the moment the parent stars died, this is where a newer idea becomes genuinely exciting. In 2025, researchers including Or Gottlieb proposed end-to-end simulations suggesting that very massive, rapidly rotating, magnetized stars could collapse in a way that naturally produces black holes inside the mass gap while also explaining unusually high spin. Their simulations start from a massive helium core and follow the collapse through black hole formation and post-collapse accretion. That is a mouthful. So here is the plain English version. Maybe the old picture treated the dying star as too simple. Maybe rotation matters more. Maybe magnetic fields matter more. Maybe the star is not just collapsing. Maybe it is collapsing, spinning, shedding mass, forming a disk, launching outflows, and rewriting the outcome in the process. The simulations report that rotation and magnetic fields can drive mass loss through winds and jet launching, allowing black holes to form within the mass gap. If you want to feel that physically, imagine an engine tearing itself apart while still spinning up its core. Some material falls inward, some gets thrown away, some angular momentum gets redistributed. The final black hole is not just the simple leftover corpse of a dead star. It is the product of a much messier, more violent process. And in those simulations, the strength of the magnetic field changes the outcome. Strong magnetic fields can pull energy and angular momentum away, suppressing how much material ultimately falls into the black hole and slowing the spin. Weaker fields allow more complete collapse and can produce heavier, faster spinning black holes. The study reports a spin-mass connection, with weaker fields permitting nearly complete collapse and spin up close to maximal values, while stronger fields lead to lighter, more slowly spinning remnants. That is a powerful idea, because it means the forbidden zone may not be forbidden in the clean, absolute way people first imagined. It may just be harder to populate unless the star arrives with the right ingredients, enough mass, enough rotation, the right magnetic environment. In other words, the gap may not be a wall, it may be a filter. And that difference changes the whole emotional texture of the story. Because now these black holes are not bizarre accidents that appeared from nowhere. They may be clues to a hidden branch of stellar death that we had not modeled fully enough. Not impossible. Just upstream of our old intuition, there is also another reason this matters. If channels like this are real, then GW 231123 is not only about one weird merger. It hints that the universe may have more ways to build giant black holes than we used to think. And that matters far beyond this one event. Intermediate mass black holes have long been one of the most frustrating missing categories in astronomy. We have lots of evidence for stellar mass black holes. We know supermassive black holes exist in galactic centers, but the middle has always felt patchier, harder to confirm, less settled. GW 231123 points straight into that middle territory. LVK explicitly describes the remnant as an intermediate mass black hole candidate formed by the merger of two mass gap black holes. That means this signal may be telling us something about a whole population we are only beginning to map. And once you let that thought in, the picture gets bigger fast. Because if massive low metallicity stars in the early universe could collapse along stranger routes than we assumed, then the young universe may have been better at making giant black holes than our simpler models suggested. That does not prove every big black hole has this origin. It does not mean the case is closed. And it definitely does not mean there is only one answer here. Even now, GW 231123 is still being discussed through multiple formation scenarios, including hierarchical mergers and more speculative possibilities. But that is exactly what makes this so good. This is science in its most alive form. Not because we found a neat answer, because one measurement forced the question to get better. That is the real thrill of space stories at this scale. You begin with something that sounds simple. Two black holes crashed. Great. Move on. But the closer you look, the less stable that simple sentence becomes. What kind of black holes? Why those masses? Why those spins? What kind of star death can make them? How often does that happen? What else have we labeled missing only because we were looking with a cleaner model than nature actually uses? And suddenly the event is no longer just a collision. It is an accusation. A tenth of a second of data pointing at a hole in the old rulebook. There is a line I keep coming back to with discoveries like this. The merger was the headline. The birth story was stranger. Because the collision itself is already absurd. Two objects more massive than 100 suns each, spiraling together in darkness, distorting space-time so violently that the signal crossed billions of light years and still left a measurable imprint on Earth. GW 231123 was detected at a luminosity distance estimated in the range of roughly 0.7 to 4.1 gigaparsecs, meaning the source lies billions of light years away. If Earth had somehow been anywhere remotely near an event like that, survive would not even be the right category. This is not a thing you watch. It is a thing that rewrites the local universe. And yet from here, from our distance, from our fragile corner of the cosmos, all we got was a faint shiver. That contrast is incredible. The loudest kind of darkness. A violent event with no light. A measurement so small it fits inside instrument noise, unless you know how to listen. And hidden inside that shiver, the suggestion that the universe is more flexible, more creative, and less obedient to our categories than we wanted it to be. That is why people love black holes, not just because they are extreme. Because every time we think we have cleaned them up into a nice final picture, they find a new way to become unsettling again. So, the next time you hear that two black holes merged, do not picture just another space explosion. Picture a forbidden band in the black hole family. Picture two objects standing inside it. Picture one clean theory after another starting to bend. And picture a species on a small planet realizing that by listening carefully enough, it had just overheard the universe doing something it thought should barely happen at all. That is the deeper payoff here. GW 231123 may turn out to be one of those discoveries that matters not because it solved a mystery, but because it exposed where the mystery really was. Not in the crash, in the birth. And that is a much stranger place to leave the story, because it means the universe may still be full of objects we called impossible, only because our imagination arrived there before our measurements did.